talk about the quantization of the electromagnetic field. So I'll go back to, we'll do a little bit more of what was in the previous chapter last time about what's the story about what's the vector potential and what's the electromagnetic field. And I'll also kind of explain, I want to kind of explain what the generalization of this is from the case of the group U1 to an arbitrary Lie group, which is an important subject. And then we'll move on to how to actually instead of quantizing the Klein-Gordon equation, to look at the equations of motion for the electromagnetic field, which are just Maxwell's equations, and then how do we quantize the solutions of Maxwell's equations, and what you end up with when you do that is basically the theory of photons. And so we'll go through that this time and on Thursday. And just one thing I kind of I realized in looking back over what I'd written about this, that I'm fairly happy with it in retrospect, except the ordering should kind of be different. The section 46.3 on kind of Gauss's law, that should actually be done later after 46.5. So I'll go through this, and I'm roughly following what's in the book and the notes, except you'll see I'm kind of skipping over one section, and then we'll get to that to next time. That whatever, I don't know what I was thinking when I wrote things in this order, but anyway, I think doing that later makes more sense. So there'll be kind of two lectures today and on Thursday about the kind of theory of pure electromagnetism. So and in some sense, physically, this is a physically trivial theory because there's no interactions. We're not talking about interactions of matter. We're just talking about pure electromagnetic fields. But it's also kind of physically kind of very, very important. What we'll be doing today is actually getting in, to really very precisely rating down, exactly what a photon is. And so not giving you some kind of vague analogy to what a photon might be, but what our best understanding of what a photon actually is. Okay, so that's the plan for today. So let me get started. So last time I talked about the vector potential. So this is something that's so x here is space and time, and it's got 4 components. Mu can be 0, 1, 2, 3. And now so you can think of this as just being kind of a 4-component field on space and time, but it has this funny property that there are these things called gauge transformations that you can add derivatives of functions to it, and it doesn't change its physical significance. And what you actually use this for is to construct to construct a so-called covariant derivative, which is dx mu minus I d. But what I want to do now first is kind of explain something about the geometrical significance about what this thing really is, because this thing is it's an example of what mathematicians call a connection, and it's also in a way quite analogous to what people use in doing general relativity and when you discuss the notion of a curved space-time. One way of thinking about that is thinking about that in terms of parallel transport, about what happens that if you're on a curved space, one way to think about what's going on is to imagine taking some frame at each point, some orthonormal frame, and then moving around in space and time, trying to carefully keep it parallel to itself. And then if the space is curved, when you come back where you started, you'll see that the frame has kind of rotated with respect to itself. Well, this is kind of the same kind of mathematics, the mathematics of a connection. It's in some sense much simpler than the mathematics of something like Riemannian geometry. What this guy is really doing is he's telling you that, in some sense, you want to keep track of the of an angle at each point in space and time. And this guy tells you kind of how to parallel transport that angle around. And that angle, in some sense, is the, if you're working with a complex field or like a wave function in quantum mechanics, that angle is just the, it's taking complex values, and that angle is an angle in the complex plane where it's taking values. So what I want to say about this is that so that you get a path dependent. So the story that I'm thinking about is that if you're in any space, but think of your nice four-dimensional space-time. If you start at some point here, and then and then follow some path in space and time to some other point, well, what you can parameterize this by some coordinates depending upon some kind of tau, some parameterization tau, and this would be, let's say this is tau. I don't want to say tau is equal to 0 and tau is equal to 1. So you've picked this curve, you've somehow picked a parameterization of it, which means you've described it this way. And then what you want to do is you want to use this, use this field, and then calculate some number based upon this thing, and it's this number. So it's going to be a path dependent dependent. I want to call this guy maybe a gamma. Is just the name of that path, and so you get a path dependent phase factor. So there's some kind of relative angle between what's going on here and what's going on there, and the way you're going to construct that relative angle is by picking a path from here to there, and then integrating this guy along the path. So in other words, you're going to take the integral. I'll write it this way: the integral of gamma a, and I'll write it as, define it as the integral from 0 to 1, the sum u equals 0 to 3. What is it? Mu d tau. So if you like, you're just thinking of this guy as a vector field, and you're just integrating this vector field along the path. Okay. Okay, and then what happens under a gauge transformation? So under a gauge transformation, I'm going to do this plus. Then what? So if you do a gauge transformation, then what happens is that the integral of gamma. So let's call this, I don't know, mu prime. The integral of gamma mu prime a prime. So if we just do the prime calculation here, if we integrate this thing along here, then what you're going to get this, you're going to get the same thing, but then you're going to have a term which is d phi dx mu times dx u d tau, but that's just that's just d phi d, integrating d phi d tau along the path, and integrating d phi d tau is just, you're integrating a total derivative, so that's just telling you the difference between phi here and phi here. So if you do that calculation, what you end up with is this is the integral of gamma a. So you get the original thing, but then this term gives you phi at gamma of 1. So I'm thinking, yeah, so anyway, so phi, or I guess I could write this as phi at x mu of 1 minus phi x mu of 0. So these path-dependent phase factors are tell you they're kind of gauge independent. They tell you they pick out a gauge independent, the gauge independent information about what AU is telling you, except that they no longer depend upon the gauge transformation anywhere along the path. They only depend upon what you're doing here and what you're doing here. Okay. Okay, and so what you can do is the okay. So now what really is so what are you going to do? I think I don't want to spend too much more time going through this whole story, but what you're going to do is you compare psi at x mu of 0 to psi at x mu of 1. So now what you're going to do, you're really, the whole point of this connection is to be able to calculate derivatives and to generalize the notion of, how do you infinitesimally translate things? How do you compare two infinitesimally close things? And what this is saying is that, well, you compare them in the usual way, except you correct by this gadget. And so if you move some infinitesimal amount away from here in some direction, then this this extra factor is going to tell you you're going to have this infinitesimal factor. And maybe a better way to say it then is that by using so what you do is you take the value of the field here, and if you want to compare it to some later point, you basically add this phase factor to the comparison. So what you want to do is compare to e to the I and the e. Anyway, the normalization for the normalization we're using, the e goes here, and then you integrate along the path a. And sorry. So if you wanted to know if the if you wanted to know if the wave function here and the wave function here were different, what you would do is you would take the wave function here and then multiply it by this phase factor, which is the extra kind of phase that you get as you move along this curve, adding up infinitesimally these little extra angles, and then you correct what this was here by that phase factor. And sorry, I guess I should say it. I should have said it the other way. So you pair this guy to this. Okay, sorry. So what you do is you take this guy here, and then you parallel transport him in the sense here, in the sense that you fix the phase by this path-dependent phase factor, and then you have something that you can compare to this guy. And then the point is that then if you do a gauge transformation here, these guys are both going to change in the same way that they're going to. So when you do a gauge transformation on this guy, he's going to pick up an extra e to the IE phi at x mu of 0. But then putting in this guy, putting in this correction factor and using this behavior, this is going to kind of fix the difference between the gauge transformations here and the gauge transformations here. You're going to get you're going to correct by this way. So this is a gauge invariant. So this is. Okay. So if you want to, this tells you how you can actually compare the values of these, let's say, these wave functions at different points in the gauge invariant way. So that's the idea. Okay. And then maybe, let's see. And then the other thing that, so now one reason for saying things like this, saying things this way, is this tells you what to do if you want to generalize from the group U of 1 to an arbitrary group. So what you want to do is you want to just kind of find if the values of these wave functions take values in some representation of some Lie group. What you want to do is you want to the correct notion of a connection is the thing that's going to tell you as you move, how to infinitesimally compare these representations at different points. So this is going to be something. It's going to be a one form, but it's going to take values in whatever the representation is that you need to act on the psi fields. So let me say what this general thing is. Generalization. So take so let so a u of x is going to be something. So it's going to still be this kind of vector field. It's going to be something which to get a value of this, what you want to do is you want to feed this some infinitesimal vector. It's going to move along, but then it's going to be element of the algebra of G, in the representation they're called pi prime. So the point is you need to know two things. What you really want to do is you want to know with these gadgets, you really like to know two things. So you'd like to know what the Lie group is you're dealing with. And so this you start out with doing this with G is equal to U1, and the Lie algebra is just the real numbers. But then you want to you also want to know what these things are going to act on, and so what kind, if you want to use these things to give you covariant derivatives of some kind of some kind of n component wave functions, that what they're going to act on. You're going to have some. Those wave functions are going to be defined to have some kind of action of the Lie group on them by some representation, and it's you want the Lie algebra elements here as matrices in this representation here that acts on psi, on phi. Okay. Well, what do you want to do is so this is kind of the general story, and this will allow you to will give you dA. Again, the formula for dA is just going to be the same thing. dA is equal to d dx mu minus I. There's an I and E, and then A. Well, actually, if you want if you take A to actually be in the Lie algebra of G, then you don't need this I anymore. But A d I E A B A U. And the point is that this acts on wave functions or field, or let's say fields if you like, using G representation. So for any zero phase. So what we did, the case that we were looking at in some sense implicitly corresponded to just looking at things in the standard representation of U1, the charge 1 representation of U1. But putting a different number here will give you a different charge. But for simplicity, so sometimes what we want to do, if we want to talk about these fields and to think about them just by themselves, and to actually like develop a quantum theory of just these fields, then we only care about, you know, that we only need to understand what value of, you know, what the Lie algebra value is for a mu of x, and we don't actually need so we might as well be in the actually maybe not. Maybe better not to say it that way. Let me anyway. Let's just. No, anyway. Okay, let me leave it like this. Okay, so maybe a better thing to do is to say this is we're going to do so we'll consider G is equal to SU2. So what I want to do is as we go through the rest of the course, I want to kind of explain how that, you know, we're going to mainly work out what happens for U1, where we can actually calculate everything. But as we go through it, I want to explain kind of what happens for our other Lie groups. But the story is really once you understand the story for the first kind of non-trivial case, the first kind of non-commutative case, which is SU2, then the general story is fairly clear about what you're going to have to do. So I'm going to write this down for the so I'm going to do this for SU2, and I guess I'll do it for SU2, you know, in the standard representation on C2. So let's just imagine that, you know, in some sense we've got so what we're going to do is instead of thinking about our fields as being kind of complex valued, and then we have to keep track of an e to the I theta of changing e to the I theta phase as you move around. Well, let's think of our fields as being C2 valued to be 2-component fields, and as we move around, and you know, depending on which path we take, you're going to have a path-dependent phase factor, and that path-dependent phase factor is going to be not an e to the I theta, but it's going to be an SU2 element, an SU2 group element. That's going to, if you want to figure out how to compare two fields at 2 points, you have to figure out what the path-dependent factor is that relates the two C2s, and it's going to be something in SU2. And so what you do then is so here now. So if you want to be more explicitly, so a u of x is going to be sum 1 to 3 of a u a of x, and then sigma a over 2. Okay. So we're using the actually, I guess I better leave this here. But anyway, so we're gonna so what we're gonna do now is the theory is going to look very much like the same as we did before, except we have to take one a mu of x function for each basis element in the Lie algebra of SU2, and in the Lie algebra of SU2 as something acting on C2. So these are just the 3 Pauli matrices. So you just take this basis for the Lie algebra of SU2, and now you've got you've got 3 components. So you basically got, instead of having one vector field, you basically got 3 vector fields, one for each value of a. And then what you do is you do dA acting on I guess sorry, there should be a mu here. Actually, I guess I wrote it this way. dA mu and is just, is something acting on side 1, side 2 is just some 1 to 3 A of x. And the story that I was telling you before about path-dependent phase factors, now you just the kind of infinitesimal change along a path is now given by this matrix here, and so you have kind of a path-dependent group element, and the infinitesimal change as you move infinitesimally is in the Lie algebra, but it's there. That's the story. Okay. And so now what we can do is we can I guess the story to say is that if you want to generalize, if you've got some kind of theory of like, for instance, if you had an n component Klein-Gordon theory, if you or a two component complex Klein-Gordon theory, if you took the standard theory of scalar fields, made it complex, and took two components. And well, you could say, well, it has this SU2 symmetry that the Hamiltonian's invariant under these SU2 transformations of the fields. What you can do is you can so-called gauge that symmetry, and then the so-called gauge symmetry version would be one where you took your original theory, and then just wherever you saw a derivative, you replace it by this covariant notion of a derivative. And then you're going to have this invariant. You're going to then have invariance of the theory under this infinite dimensional gauge group. And then you do the same thing as to get the field strength, the analog of the E's and B fields. The reason I gave us a definition of that in the U1 case in terms of the commutator of covariant derivatives is that also works in this case. And so what you do is you say that the field strength or the curvature, depending upon what language you want to use, is given by this guy. You just take, well, let me do it I over E, and you take the you take the commutator of these guys, and then now you get something which is so these are going to be matrix. These are going to be these are now matrix value things. So you're going to get some kind of 2x2 matrix value thing. It depends upon mu and nu, and you write that out with respect to this basis. And so you write it this way. It's sum from A equal 1 to 3 of F mu nu A times the sigma A over 2. The point is, so these guys are giving you something. Each of these is giving you something in the Lie algebra of SU2. And so if you take the commutator, you're getting something in the Lie algebra of SU2. So it's a 2x2 complex matrix given, with and so written out with respect to this basis of Pauli matrices, it's given by these guys. So this is the same story as I told you about F mu nu. There you just had one component. Now you've got three components. So this theory is a theory where you've got now three component vector potentials that now carry an extra index going from 1 to 3, and they've got corresponding field strengths, which depend upon these kind of antisymmetric tensors in mu and nu, but they also have three components also, which are labeled by by this A. Okay, and then what you want to do, okay, so then your problem is how do you, if you remember what I did, you can then write this out more explicitly, what the formula for this guy is in terms of these guys. And let me write down those formulas. So you get so for the various so these mu and nus, you separate out what's going to happen for the case where one of them is 0 and where the case where neither of them is 0. And if one of them is 0, you get F0J, and that's what you call the electric field. Except now it's but you have to remember this guy now is a 2x2 matrix, so you would write him as the sum E J, but there's an A times sigma A over 2. And if you write this thing, and if you write this, if you write out what this definition tells you, it's going to be minus BA J dt. Whereas this is, remember, this is now a 2x2 matrix, plus the A0 dxj. And this is the usual formula for the electric field. Okay, this is, but the only difference here now is is that these things are now 2x2 matrices. But the problem is that there's an extra factor that when you dealt with the electromagnetic field, and if you computed this, there was a commutator of the A's with themselves. There's a commutator of A mu and A nu term, and that was 0 if the if the A mu's were just numbers that commuted with each other. But now the A mu's are matrices, so you get an extra term which is minus I E AJ J A0, and you get the same thing for the epsilon J K L F K L. You get the same thing. You can also define a magnetic field in a similar way, except that now it's a 2x2. It's a 2x2 Hermitian matrix. So it's 3 over 2, and you get the same formula. What you get is you get epsilon JKL, and then a D A L DXK D A A. And so this is just the usual formula for the for a magnetic field in terms of the A's. But you also now have an extra term, which is this guy, A L. Okay, so this is this is kind of the generalization of electromagnetism, and this is what's called Yang-Mills theory. This setup here, and it was first. So people first figured out during the 50s. It was C and Yang and Mills, and actually Pauli I think had first written down this theory. But then the question was that if you want to if you kind of want to generalize the theory of photons, the theory of electromagnetism, which we're going to discuss later, how would you actually what does that actually look like? And what people realized was that if you take if you take E to 0, if E is small, and you don't have to worry about these terms, then it's basically just 3 copies of the theory of electromagnetism. You've just written down 3 non-interacting copies of the theory of electromagnetism. But your problem, but the problem is that the problem is these extra terms, and these terms are the things that are going to cause. I mean, we won't are going to be making these make. Let me just say that these make the equations of motion and nonlinear. So we'll see that a little bit more maybe in a minute. But basically, if you take H, your Hamiltonian is the sum 1 to 3 of E. Well, E A vector squared plus A vector squared. If you try and just take the standard Hamiltonian that you used for the U1 theory, which we'll talk about some more in a minute, then you the problem is that you end up with these guys, just like electromagnetism, give you terms that are quadratic in the in your fields, in the A fields, and so you have a quadratic Hamiltonian, and you can use all of our standard methods to deal with it and solve the theory. But these terms here give you terms that are cubic and quartic in the A's, and so you've got a Hamiltonian which no longer fits into our kind of nice reduce everything to a harmonic oscillator story. So it's still, I mean, actually, I'll say some more about this as we go along, but it's still kind of, in some sense, it's still kind of an open problem exactly, how to exactly solve this theory and say precisely what's going on in it for due to these nonlinearities. Okay. So maybe that's about all I want to say. But the anyway, but what I wanted to say mainly was just to give you this kind of geometric way of thinking about what a gauge theory is, and to see that you can do it for any Lie group, and that this is going to turn out to be quite important for the standard model in physics. But the minute you get beyond, what we're going to do now is we're going to go back to U1, and then in the case of U1, we can exactly solve this theory, and we can tell you. But in the case of the minute you go to something non-abelian, these terms are kind of wreck the methods that we're going to use to exactly solve the theory. Okay, so this in some sense is kind of just the geometry and setting up the basic fields. And now when I kind of go on to the equations of motion and quantization, but is there any questions about this stuff, or about this? This is just the beginning of a long story about so-called gauge theory or Yang-Mills theory. Okay, so then if not, I'll go on to we'll go back to U1 and actually tell you how to spend the rest of this lecture and next time showing you how to quantize the U1 theory. Okay, so back to okay. So back to U1. And we've got, so now remember our basic fields are something I'll call A0, depending on time and space, and something, and then some maybe let me just write it this way, then vector. Okay, so these are our basic fields, our vector potentials, and then we kind of took field strengths in terms of these. We formed some gauge invariant combinations of these things, which are the electric and magnetic field strengths, and they're given by, so E vector, this I did last time, it's minus dA dt plus the gradient of A 0, and then B vector is equal to curl of A. So this is just standard electromagnetism about what the electric field is and what the magnetic field is in terms of the vector potential. Okay, let's see now. So these are our fields, but we want them. We want to give them some dynamics. So we want these things to satisfy some kind of equations of motion. So there's going to be some partial differential equations which these things satisfy, which are going to tell us, if you know what the state of the world is at a given time, how it's going to evolve later. And so what you want to do is these are Maxwell's equations. And remember these. So what we're doing is something physically relatively trivial. We're just considering the so-called vacuum. So there's no, at this point, there's no charged particles or anything floating around. There's just electromagnetic fields. So this is going to describe things like, light rays moving around, but it's not, there are not going to be any charges moving around. So, okay, and so let me just write these things down. That they're in every. I hope you've seen these. They're in every electromagnetism book. Vector dt and vector dt, and then del. Okay, so these are Maxwell's equations, and they have somewhat different nature. One thing to notice is that so these two are really automatic from the definition. These in some sense are not telling you anything new, because you knew that you knew that B was the curl of A. But this one is automatic because if you take the divergence of a curl A is equal to 0 for any So this relation that the divergence of B is 0, it's automatic from the definition of B. No matter what, every A is going to satisfy this equation. It's telling you nothing new. And similarly for this one, let's see, and then then this one is yeah, okay. Anyway, let me not write this then. But this is also automatic. This is automatic because of you can reduce this equation to the curl of a gradient of some function. And so if you just play with this a little bit and rewrite it, you'll see it's the curl of use the fact that B is the curl of A and rewrite this. You'll write it as the curl of something, and that something is a gradient, and the curl of a gradient is always 0. Okay, so these guys have this weird feature that they're just automatic. And I said something before about the if you've seen this theory of differential forms, which is very, very nice here, then in terms of differential forms, you have that F, you have that the F is a 2 form, and it's this thing called the de D applied to a 1 form. And then these guys are basically the equation dF is equal to 0, but it's automatic since this guy has the basic property that d squared, that if you do it twice, you get 0. Okay? So if you study differential forms, you should recognize these formulas for E and B, and the field strength in terms of A are just the de Rham derivative of a 1 form A. But and these equations are basically, you're taking the de Rham derivative of a 2 form, and if that 2 form is of the form dA, then it has to be 0. Just okay. So that's that. And now the so the equations that are non-trivial are these guys. So we have to set whatever kind of formalism we're going to set up. Either we have to come up with a Lagrangian whose order of the Lagrange equations are these guys, or we have to come up with a Hamiltonian system whose Hamiltonian is gives you these guys. And this one is this one is going to have a peculiar status that we're going to encounter as we go on. And so this one is called Gauss's law. So we're going to have to, but anyway, we're going to, so our non-trivial equations of motion are basically these guys. And we've got to somehow, we've got to somehow implement these guys. And normally we're doing kind of Hamiltonian mechanics. So you want to find a Hamiltonian that such that the Hamilton's equations are these guys. Okay. Okay, so let me tell you about the Hamiltonian formalism then. So there's something. Okay, so let's start. But remember what we're trying to do. So in some sense, we're trying to develop a Hamiltonian formalism, put those equations of motion into this Hamiltonian formalism, and identify what the phase space is, which is going to be the thing that parameterizes the solution's equation of motion. And then that phase space, we then want to quantize using harmonic oscillator methods. That's the whole plan. But okay, so what we want to do is we want to find identify by M, which is the dual, if you like, the dual of the dual of the phase space of solutions, and so M is the phase space is equal to space of solutions, and that's like. So Maxwell's equations are second order equations. So what you normally do is you use initial data. So you want to parameterize M. We'd like to parameterize M by initial data. And so it's a second order equation. So what you want to do is you want to take a 0 at 0, and then let's say a vector at 0, x vector. So you want to take the values of the fields at time 0, but it's a second order equation. So to specify a solution, you also need the derivatives. You need to specify the first derivative. And so these are going to be your kind of configuration variables, space variables like your Q's, and these are going to be your momentum space variables are more like your P's. And then, but you want to just kind of say that this is a same thing you would do with Q's and P's, except there's an infinite number of them. This is what you'd like to do. Okay, now here's the problem. This is the basic. So this problem appears in different ways depending upon how you decide to define the theory or to quantize the theory. But this is this I think this is the way that it appears from in the Hamiltonian formalism. Here's the problem is that the Maxwell's equations are gauge invariant. You know, anyway, so if A is a solution, well, you know, so is the A. Well, so is the gauge transform A. Okay, and then okay, so there's this huge inferential group acting on the solutions, and okay, so that's something to keep in mind. But especially problematic is that if you so the problem is this doesn't uniquely specify a solution, since you can gauge transform by phi at phi is equal to 0 at t equals 0. Yeah, and get a new solution, same initial data. So the whole point of I mean, kind of at the basis of being able to use to do Hamiltonian mechanics is that the point is that the phase space is supposed to be a unique one-to-one. It uniquely parameterizes solutions. But the problem is that if you just say, okay, well, I know that your solutions are solutions of a PDE, so I'm going to parameterize them by their values at t is equal to 0. The problem is that you in this kind of theory, you don't have a unique solution with this data. So if you find one solution with this data, and then you can pick any kind of gauge transformation as long as it's 0 and t is equal to 0, but it can be some complicated non-zero function everywhere else, and you'll get some completely different looking thing, which will have the same initial data, and which will also be a solution of the equations of motion. So this data, this data parameterizes an infinite number of solutions, not one solution. So this is kind of the fundamental problem. The fundamental problem that the Hamiltonian formalism is just not going to work the way that you would like it to work. Okay, so what can you do about this? So what can you do? Well, there's two strategies. One is what we call gauge fixing. And what this means is you impose extra conditions on a mu of x, that remove the gauge freedom. So what I'll show you what ones work nicely, but there's in some sense an infinite number of different ways of doing this, but it's called gauge fixing. Is that we're going to make some extra choice, which we're going to impose. Say, well, we're not going to look at all possible a mu's. We're just going to look at all possible a mu's that satisfy a certain condition. And that condition is set up so that it's going to get rid of this problem of an infinite number of solutions corresponding to the same initial data. We're going to chain. We're going to show that there's only one possible solution that satisfies, that has that initial data and satisfies the gauge condition. So that's the plan. So that's what I'm going to talk about today, the rest of the day, about how to do that. And the second one, the second idea is to quantize all A's, all solutions, and then impose a condition on the states that making them gauge invariant. And so, in some sense, what we're doing here is this is called find the gauge invariant piece of the story of the A's first, and then quantize that. This is called gauge fix first. Take gauge invariance first, then quantize. This is the opposite. You quantize the whole thing and then look for a gauge invariant piece. And so so these are the two kinds of strategies that get used in this story. And today we'll concentrate on this one. I'll say some more next time about this one. Okay, so the first, okay, so we're gonna, it turns out if we're gonna do one, but the first step, so it turns out to do this, you have to do first step. You have to do this in two steps. First step is impose A0 equals 0. So we're going to look at we're going to look at gauge potentials at vector potentials whose time component is 0. And the point is just that you can always find you can always find phi such that if you start with any A0 and gauge trans and choose this and choose phi appropriately, you can make the 0 component 0. And so I think I've wrote this as that phi such that gauge transform A is 0 by, and it's just phi of, you take phi of t and x, and you basically you integrate from 0 to t a of tau x vector A0 of that, etc. Okay, and then plus, well, anyway, d tau, and then anyway plus whatever you had. It is at 0. So you just pick. You choose a gauge function phi, which could be anything at t is equal to 0, and then at other times you just make it the integral of A0, And then when you if you compute what this gauge transformation does to this guy, basically you're going to get a term, A0 is going to change by the time derivative of phi, and you take the time derivative here, you're just going to get back A0, and you're going to cancel your original A0 and get A0 equals 0 as your gauge transform. So this is called temporal gauge. And the same trick also works. This doesn't care about whether it's U1 or any group. This also works for Yang-Mills theory. You can do the same thing for Yang-Mills theory. Okay. Now so we're going to work in temporal gauge, where so the A0 is 0. So now what we want to do is we want to so now we have so now our coordinates on the phase space are just the A vector at x vector at time 0 and its time derivative. Okay. And then remember E vector, the formula for the electric field. Now you lose the term that has an A0 in it, and you just have this term is minus the A vector dt. Okay. So your phase space. So if you like your phase space coordinates, you can also think of them as being this A vector at this time 0, and then the corresponding kind of momentum is the derivative. So just as, and so you want to take this to be you want to fix the minus sign here. You want to take it as minus E vector x vector. Okay. So you can think of the initial data in this temporal gauge as being your configuration space data, just the spatial components of the vector potential, but then also the corresponding momenta, which are the minus the E vector of x vector. Okay, so these are your analogs of your Q's. These are analogs of your P's. And now you can go ahead and try and quantize. Okay, but then your problem is that there's still. Let me see what I want to. Okay. Oh, and then you can do maybe just to write down the entire. Let me just quickly write down what the Hamiltonian formalism is. Then it's just really that. So classically. What you have is you have this phase space that that all of the Poisson brackets are 0 except the Aj of x vector Ek of x vector prime, and that's just that there's a delta Jk and a delta of x vector minus x vector prime, and then there's a minus sign because of this. So these are kind of distributional formulas, but this is the Poisson bracket on these things, and then the Hamiltonian that's going to give you the Hamiltonian is going to be a half integral of r cubed E vector squared plus B squared. That's the Hamiltonian function on the space, and then what you do is you find the and then I won't write this down, but then Hamilton's equations become the same thing as the Maxwell equation. Okay. Oh no. But okay. But here's our problem. Okay. But Maxwell's equation, d e dt. Yeah. Okay. So let me write down the Hamilton's equation. So Hamilton's equation are d a dt is equal to a h. But if you compute that, you'll get minus e vector. So that's just the definition that the the momentum is dq dt. But then if you do the you get e vector h, and then you get if you compute this, you get the. But this is one of the Maxwell equations. So remember, there are two non-trivial Maxwell equations, which we have to somehow satisfy. So what we did if we set this formalism up this way, we get the we get one of the Maxwell equations. Okay, so the problem is then though that we don't have there's a missing equation, which is Gauss's law. So the problem with this formalism right now is that this this doesn't have Gauss's law. Okay, so Gauss's law, which was the second non-trivial Maxwell equation, it's not imposed by here. So the formalism we've set up, it's a perfectly nice formalism, but it doesn't actually it doesn't impose one of the equations we want. It has too much. Anyway, it in some sense it is much bigger than the real space of solutions of it's the space of solutions of Maxwell equations if you didn't know Gauss's law, which is something bigger than what we want. And so our problem was that we still have time independent gauge transformations. That can acting on the phase space. So and what we thought was our phase space. The problem is that we actually haven't gotten rid of all. We haven't completely gauge fixed. We've only kind of partially gauge fixed. We've still got lots of solutions that are related by gauge transformations, and so we need step 2. And this is what's called. And so now what you do is you impose Coulomb gauge. You impose an extra condition. This is the Coulomb gauge condition. The gradient, that the divergence of A is 0. And so what you want to do is so you need to find under a gauge transform, right, under a gauge transformation, what you need to do is you need to find you can compute what this does. It goes to it's the same thing plus another term, which is the derivative squared of phi. So what you want to do is if you start with some arbitrary a, you want to find a phi, you know, such that this guy satisfies this condition. Okay? And so so you can find phi. So you solve phi grad squared phi is minus this guy. Okay. And then you can use this to get to Coulomb gauge. Okay. And so you have to look a little bit about at the theory of PDEs, and you can show that that there is a unique solution to that if you start with a vector potential that's got del dot A non equal to 0 to some function, you can solve this. You can solve this kind of Poisson equation, I guess it's called. You can solve this Poisson equation, and it has a unique solution under reasonable conditions, and that's what it's going to do this. And so the thing to notice is that here I've actually crucially used the fact that it's U1. We're in the abelian case. So in the non-abelian case, this doesn't. There's a much more complicated story, and it's called the Gribov ambiguity. So in the one thing that makes the Yang-Mills theory much harder is not just that the dynamics is the Hamiltonian is not quadratic, but also that this nice gauge fixing that we're going to do, which is going to give us a nice gauge fix theory where the Hamiltonian formula is really going to work. That's actually doesn't something much more complicated and confusing happens there, because you end up with this solution is a nonlinear equation with lots of solutions, not just a linear equation with a single solution. Okay, let's see. Okay. Okay, so now, so what we're going to do now is we're going to impose these two conditions. The I guess I better. Sorry. Well, anyway, so the condition is going to be, we've got rid of the A zeros by some gauge transformation. We've done another gauge transformation, so we've satisfied this. And so now, you can look and see what the anyway, and imposing that condition is going to get rid of our Gauss's law problem, but what the okay, let's see, 46. Yeah. So in okay, so that solves our Gauss's, that gets rid of our Gauss's law problem and is going to give you Gauss's law. But what you also have, but now the one, so the equation of motion, yeah. That's left. Yes, so this is the thing which I guess I wrote it. This is the thing which you get from. So it's a del. It's this one. So this is the one that you get. That's our Hamiltonian formulas of now. This is the one of so this is Hamilton's equation. So it's a Hamilton's equation for that Hamiltonian that I wrote down. But now what we want to do is I want to, let's see, okay, here we are. Okay, so but now let's write it out in terms of A. So it's so writing it out in terms of A, it's d dt. This guy is the dAdt. So you get a minus p squared A vector dt squared. That comes from this side of the equation, and this guy you can write as a curl of A. And then if you use a what you find that this is use some vector calculus, and this is the gradient of del of the divergence minus A. And so what? And then you use the fact that the Coulomb gauge condition says that this is equal to 0. And so what you end up with is d squared dt squared minus squared A vector is equal to 0. So this is your non-trivial Maxwell's equation in terms of A, or if you like the Hamilton's equation for that standard, for that Hamiltonian E squared plus B squared. But now on a phase space, and your phase space is the so M is the A vector, an X vector, the it's called E vector, X vector, and then status such that So this is what your phase space is. It's pairs of functions of three dimensions where this one satisfies this equation, and this is going to give you additional data for this equation. So this is going to anyway, and so this is going to be dAdt. So what all you really need to do is look at solutions. So this is just 3 copies of the wave equation, right? So this is just the standard wave equation, or if you like standard Klein-Gordon equation, standard relativistic Klein-Gordon equation. But you just got 3 copies, and the only funny thing that's going on is that it is this condition. So let me kind of stop here, but just say in words what you do with this. And so what you do with this is you just quantize as 3 copies of the scalar field theory. Plus, plus one condition. So condition that P vector with right. So if you take the Coulomb gauge condition and go to momentum space and Fourier transform everything, so it should be a Fourier transform. Well, it's got 3 components, but the component in the p direction is 0. So so it's 3 copies. So the component. So and so what you do is you say that A J tilde of P vector is what's called transverse. Okay. So you thought you were quantizing a theory of just kind of these vector fields of just 3 copies of the Klein-Gordon equation. But really there's this, because of this extra condition, it really is just for each p. It's just a bunch of oscillators. It's just it's just a bunch of harmonic oscillators, one for each p. But for each p, there's you thought you had 3 harmonic oscillators, but you really only have 2 harmonic oscillators. You only have the 2 directions that are this vector field can only really move in the 2 directions that are perpendicular to that value of p. Okay. And so, and maybe the just in words, so you get for each p vector, you get two scalar fields. And, you know, the two transverse fields, and these are going to be the photons. Okay, so I'll start next time by saying a bit more about how this works. But in some sense, it's really just writing down all the same equations that we wrote down. Write down 3 copies of all the equations that you wrote down for the scalar field, and then if you just did that, you would say, "Aha! I've got a theory where for each value of the momentum, I've got kind of 3 possible kinds of particles, if you like, and I can have and I've got a quantum field theory. It tells me how to make a theory of of any number of these particles, and using one harmonic oscillator for each p, and you're just done. But then you have to say, but wait a minute, there is this one extra condition, which says that one of those 3 for each p of those 3 possible particles, that 2 of them were one of them was moving along the same direction as p, and that guy you had to get rid of. That's sometimes called a longitudinal photon, and so that degree of freedom has to be eliminated, and that's because of that gauge condition. But you still have 2 of them, and you have these 2 kind of transverse degrees of freedom of the photon for each p. Photons can be, they can be right circularly polarized or left circular polarized. They can go in polarization either direction. So let me stop now. So I'll write that down more explicitly next time, and then say some more about something. So one, but just to say one of the problems with this whole setup, you find, is that that we're going to get to next time, is that this whole setup is not Lorentz invariant. So that when I chose time like gauge, I chose a specific direction of time, but then when I chose this Coulomb gauge condition, that's also not a condition which, if I do a Lorentz transformation if I put something in Coulomb gauge and do a Lorentz transformation, it's no longer in Coulomb gauge. So this setup works very, very nicely. This is called a physical gauge. It puts everything exactly in the standard formalism of the Klein-Gordon equation, but it's got it's got peculiar properties because you're basically violating, you're basically, in order to get the Hamiltonian formalism to work, you're violating Lorentz invariance, and so your formulas are now all, it's very, very unclear why the theory should be Lorentz invariant, and you have to show that that's true. And so what I'll do next time is maybe talk about it some different ways of, first of all, we'll work this out a little bit more detail, and then explain how some other formalisms that you can use, some other ways of dealing with the gauge problem, which allow you to kind of try and maintain Lorentz invariance. But then those will have other problems. We'll see. Okay. So any questions about any of this stuff now? I mean, it's kind of, so this is anyway, it's fairly, the problem, I mean, the quantization of this Maxwell's equations is in some sense a fairly straightforward story, except for this gauge invariance is really just what causes all sorts of trouble. All of the standard And if you do this, if you say, well, okay, let's not use the Hamiltonian formalism, let's use the Lagrangian formalism, you really kind of can't avoid the problems if you anyway. So if you look in a standard field theory textbook that tries to do a Lagrangian formalism, a path integral formalism, you'll find that you just you end up seeing the same problems. In some sense, your path integral is trying to integrate over this infinite dimensional. You have kind of infinitely more things than you physically want, and your path integral is integrating over way too much, and so you have to somehow do something like gauge fixing or something to restrict your path integral. But so this isn't anyway. The gauge freedom problem is a really nasty problem. It's not so bad here. You can actually deal with it and understand what happens in the theory of photons. It becomes a it becomes kind of a truly horrific problem if you deal in Yang-Mills theory, because of the these gauge conditions now become nonlinear, and you've got all sorts, and trying to solve them, you get all sorts of weird solutions and all sorts of trouble. Okay. But any other questions right now? Okay, well, if not, I'll cut this off now. But yeah, I'm definitely around, and please come back and talk and talk to me on the other Zoom thing. Okay, and bye now.
Thank you very much.
All right.